Hello everybody, once again. Hope you're doing well. This video, as the title blares at you, is concerned with the roots of polar complex numbers and how do we find them. Okay, so that's what we're going to talk about. How do you find the roots of polar complex numbers? And I would recommend that you have nearby you somewhere as you're watching this a written down version of de Moivre's theorem. It will prove useful at one point. Okay, so you might want to dig that up and have it nearby. Okay, we're going to start off this video with some rather tough, as in tough to understand sentences. Okay, some little bit thick language here. So get ready. If z is a complex number and w is an nth root of z, then that means that w to the n equals z. And furthermore, that n such numbers exist. That is, nth roots exist. Okay, now that may be a little bit tough, especially that last little comment there, n such numbers exist, but that may seem completely bizarre. Let's do another example, a little short example to handle at least the first part. So z, let's say, equals 8i, a nice easy complex number like that. And let's deal with the cube roots of 8i. Well, since negative 2i to the third equals 8i, that means that 2i is a cube root of 8i. Okay, so think about that for a second. Hopefully it makes some sense. But furthermore, there are two more cube roots of 8i, and that may seem rather strange. But that is what we're dealing with here. In fact, these extra roots, the ones that are less obvious, that is really kind of where the tough work of finding the roots of polar complex numbers is in this finding those extra roots. Okay, so those were a couple of tough sentences. Here is another one. If w to the n equals z, then z to the 1 over n equals w. Now, if you think about that, maybe that's not so bad. Put in an easy number, like 2 to the 5th equals 32. Well, that means then 32 to the 1 over 5 equals 2. Okay, so you can come up with some numerical examples like that help that idea make sense. So anyway, if z is equal to r cosine theta plus I sine theta, in other words, if z is a complex number in polar form, all right, and w is an nth root of z, which is, by the way, that's what we're trying to find, right, is these nth root of z. So if w is an nth root of z, that means that w equals z to the 1 over n, all right? Okay, so hopefully that, I'm building a little chain of logic here, I hope. So yes, w equals z to the 1 over n. W is an nth root of z. That's what we're looking for. Okay, so here's how we find it. Here is the formula for finding z to the 1 over n. So look at that there, and now check out your de Moivre's theorem sitting next to you, hopefully. Look how similar they are. They're very, very similar structures. Yes, that argument there, here in front of you, is kind of a mess, but it's essentially just theta divided by n. And it's theta plus 2 pi k, actually, divided by n. But you know, that's what we're going to do. We're going to, instead of multiplying theta by n, as we do with de Moivre's theorem, we're going to divide. Because we're kind of going the other way here. Instead of finding powers, we're finding roots. So it really does kind of make sense. And hopefully it does start to make sense, even if this is your very first time ever seeing stuff like this. However, if it's still rather foggy, which is perfectly understandable, do not despair. You can always replay the video, but actually I have summarized, hopefully rather succinctly, the steps to finding polar complex numbers polar complex roots in the next slide. Anyway, here, take a look at this. To find the nth roots of a complex number in polar form, follow these easy steps. First, find r to the 1 over n. Now, that's not too bad. Then find theta divided by n. Well, that's also not too bad. And then finally, we add 2 pi over n minus 1 times. Okay, now that's may seem a little odd because it's a new thing for us, but that's what we're going to do. I'll show you how this works in an example, all right? So let's say we are going to find the fifth roots of 32 cosine pi over 2 plus I sine pi over 2. So So we're not messing around here with something really baby stuff. We're finding the fifth roots of that number, which is actually helpfully already in polar form. A little asterisk here, if the number you are given is not in polar form, in other words, it's in rectangular a plus bi form, you must first convert it into polar form in order to take advantage of this method. Okay, so first we find r to the 1 over n. Well, what's n? N is 5. We're finding the fifth roots, so n is 5. Okay, so 32 to the 1 over 5 equals 2. Well, that was pretty easy, wasn't it? Okay, next step, find theta divided by n. Okay, well, actually, that's not so bad either, right? Because theta equals pi over 2. Pi over 2 divided by 5 equals pi over 10. Wow! Well, that's really great, okay? The next step is to add 2 pi over n minus 1 times. Okay, well, just think about that. I mean, that literally is what we're going to do. Let's just think about how it works. 2 pi over n means 2 pi over 5, right? Which I'm going to convert that to 4 pi over 10 because I'm going to add it to pi over 10. So that way I have a nice common denominator there. Now n minus 1 times, well, that equals 4, right? N equals 5, so n minus 1 is 4. So we're going to add 4 pi over 10 to our theta, pi over 10. We're going to add that 4 times, okay? So we start off with pi over 10. Now we add 4 pi over 10. That's 5 pi over 10. This really isn't that hard, is it? That's 1 time. Now we're going to add it 1 more time. 9 pi over 10. All right, I keep adding 4 pi over 10. So I've done it 1 time, I've done it 2 times, I'm going to do it 2 more times. That'll be 13 pi over 10 and 17 pi over 10. And look, I've got 5 different numbers there. I've got 5 different angles that represent the 5 different fifth roots of the number that we started with, that 32 cosine pi over 2 I sine pi over 2. Okay? So all I have to do, I've literally done all the work by now, except for just kind of putting the whole collection into its structured form there of the polar form of a complex number. And, oh yeah, I'm going to change 5 pi over 10 to pi over 2 just for simplicity there. But here are the roots. Okay, I'm not going to read them out to you. You can read them. You can see how they're showing up there on this screen. But it's all 5 of them. And they do look pretty impressive, I must say, once you get them all stacked up on top of each other like that. But there they are. That's the 5 roots. Really, all we did was find r once, and then we found theta pretty easily, and then just added this 2 pi over n to theta the proper number of times so that we end up with the proper number of roots. Okay? That's the process. Go back and check it out. There's a couple in the book that are a little bit different, but they do exactly the same thing. And so by all means, practice, read carefully, and do your best and have some fun doing some really interesting and unusual mathematics. Bye-bye.